Okay, my turn, I guess. My name is Stephen Burke. I have my PhD from Lund University in the Department of Building Physics, and I work as a qualified technical specialist at NCC. And I'm going to talk to you a bit about thermal bridges, theory and standards. Talk about a little bit about the theory of thermal bridges and what kind of standards there are today that you can use to help calculate thermal bridges. I'm going to go through what a thermal bridge is, so we're all on the same page, because as you hear from Björn a little bit later, different people have different ideas about what a thermal bridge is. So it's important that we're on the same page. And then I'm also going to look at the different standards that pertain to thermal bridges, to describe how we calculate them and different parameters we should use. So the first thing we need to know is, what is a thermal bridge? Well, according to the ISO standard 10211, a thermal bridge is defined as a part of the building envelope where the otherwise uniform thermal resistance is significantly changed by full or partial penetration of the building envelope by materials with a different thermal conductivity, and or a change in thickness of the fabric of the building envelope, and or a difference between internal and external areas, which occurs, for example, at a wall, floor, and ceiling junctions. So all this is saying basically is that a thermal bridge is anywhere on a building where heat can escape more quickly than the surrounding materials and constructions. And so, just to show a little bit of a visual picture of what a thermal bridge is, we have a wall in the first image which is completely uniform. We'll just assume it's concrete and insulation. We have the same heat transport through the whole wall. Just by adding a floor to this concrete wall, we affect the heat transport from the inside to the outside. So even this here case is a small thermal bridge, and we can calculate the change in heat transport between the first case with nothing and the second case with the floor added. The third case is a more clear example of a thermal bridge where we have the concrete slab coming out into the insulation layer. So here we have a thinner insulation layer, and you can see that the heat transport through this construction is much quicker than just through the normal wall. And then the last one we can have is a geometrical thermal bridge where we have a corner, for example. And in this case, we get an increased heat transport out through the corner of the construction, even though the insulation is uniform through the whole wall. And this is another example of a thermal bridge. So basically, this is what a thermal bridge is about. It's not about wind transport or air transport. It's purely about heat transport. So a little quick question about why are thermal bridges so important? Well, from an energy perspective, it affects the energy calculations. In low energy houses, it becomes even more important to take into account thermal bridges because they represent a larger percent of the total heat loss. From moisture risks, we can have mold problems, condensation problems. It can affect the indoor environment, the health of the people living there. And it can even affect the durability of building materials. Materials start breaking down quicker than they should. Some of these thermal bridges can be fixed if you already calculate them in the design phase. And thermal bridges can be used as a sort of quality control if you use thermography. And to verify thermal bridges after the construction phase, you can see using calculations and thermography which thermal bridges are supposed to be there, which temperatures should we have, and if they vary a lot with the thermography, you may have a situation where there has been some kind of cheating going on, or they forgot to put insulation in or maybe other problems like wet insulation materials. So you can use thermal bridges and thermal bridge calculations for quite a bit of different uses. There's quite a few standards involved here. Here we have an EN ISO 13790, which is about energy calculations. And around this standard, we have a bunch of different standards which can affect the energy use. We're going to go through a little bit of these standards and what they say and which ones are most important for thermal bridge calculations. So we have a number of different ones, EN 6946, that looks at thermal resistance and thermal transmittance, different material layers and properties. That's quite a useful one. I'm going to show you a little bit later how, especially when dealing with the air layers. We also have 7345, which talks about the physical quantities and definitions of thermal insulation. We have 10177, which talks about the thermal performance of windows and doors and shutters. So it's how you would calculate those things. The most important one that we use when we're doing energy calculations is the 10211, which shows you how you should calculate thermal bridges in building constructions. Which I'm also going to show you a little bit more. 10456, don't use too much hydrothermal properties and thermal performance of buildings. Heat transfer via the ground is also there. And then we have a few other thermal bridges, but some of them are not as useful for thermal bridge calculations. They're more related to energies. One important thing when you're doing thermal bridges is you need to have a little bit of a check on the air layers. And 6946 helps you by providing different surface resistances. You can use your RSI and your RSE depending on the heat flow. For example, if you had a ceiling or a floor or a wall, you have different RSIs. The RSE is generally the same because it's based on an average wind speed outside. You can calculate RSE for different wind speeds and things like that if you want to. One nice thing here is they have a little bit of a table with thicknesses of air layers where you can have thermal resistance of this air layer. That can be good to put into calculation if you need to. Generally, we try and avoid air layers. If we have a ventilated facade, for example, in Sweden, we generally just put the RSE is equal to the RSI, and then we don't bother simulating the brick, for example, a ventilated brick. When we look at our heat transfer, we have a bunch of different variables. The total transfer is equal to the direct transmission plus the ground transmission plus the unconditioned space plus the adjacent buildings. And basically, the thermal bridges fall into the HD category, which is direct transmission. And the direct transmission is a combination of the U times A of all the building components plus the linear thermal bridges plus the point thermal bridges. And I'm going to show you now what the difference is between a linear and a point thermal bridge. A linear thermal bridge is a thermal bridge that continues along a line. One example is the floor wall connection, where you have that goes all the way around the building. That's an example of a linear thermal bridge. Another one can be, for example, a window frame that you see in this picture here connected to an external wall. The second example in the picture is actually the wall connection to the ceiling. That's also a linear thermal bridge. So it has a certain length. Usually it's the perimeter of the building or the perimeter of the window. And basically, to get the thermal bridge, what we do is we calculate the L2D, which is the actual model in 2 dimensions. And then we subtract different reference calculations, we call it, Uj times L, which is the thermal transmittance of the 1D components times the length. And I'm going to show that a little bit in a few seconds. A point thermal bridge is a three-dimensional thermal bridge, and in this example we can see there's an I-beam coming out through a concrete slab. But this concrete has, in theory, insulation between it, so it's not a very big thermal bridge, but this I-beam coming through is an example of a point thermal bridge. So in this case, we calculate the thermal bridge for the I-beam construction and not a certain length. So basically that's what this equation is saying, where we take the 3D model and then we subtract the different U in areas for the adjacent walls, like the theoretical U times A. According to the 10211 for linear thermal bridge for floor, we make an original model, so like I said, and we calculate that. And we have a little bit of requirements as well, like the line A has to be longer than 1 meter or 3 times the thickness of the wall. And it should be the same length above and below the thermal bridge point, and that's so that you don't get numerical errors. In the reference model, you make the reference model walls the same length as in the LTD model. But here you can see that it's just a pure cut of the wall where you have insulation. You don't have any studs, for example. In the ground, it's a little bit different. You make the L2D model the same as what you have on paper. And then for the earth, you need to have at least 2.5 times the width of the building in soil to take into account the insulation effect of the ground. So a little bit of a close-up here. You can see we have A again and B. A is the internal height from the floor, and B is the internal width of the building. Same rules for the wall height and stuff as well. 1 meter or three times the width of the wall. When we do the reference calculation in the ground, we actually need to move up the floor slab so that it sits on top of the ground. And then we put in a open boundary line segment, which is a zero flow through C and even through boundary 4 here. So all the heat transport goes down through B. And that's one of the reference models. And then the other reference model is the actual wall, same height as in the original model. So then you take the original model minus the 2 reference values, and you have your thermal bridge. Corners is the same kind of method where you simulate your 2D model and then you subtract the 2 reference cases. And a simplified window calculation basically is the same idea, where you make your 2-dimensional model and you subtract the 2 reference values, which is the pure wall and the window and frame. So that would be the thermal bridge of the window connection, not necessarily the window frame. That would be a different calculation. The last thing I wanted to show you was that in the ISO 14683 standard, they actually have simplified methods and default values. So if you're not able to calculate thermal bridges or you have trouble with it, you can get approximate thermal bridges from this standard. We don't generally use this standard at all. Within NCC, we always calculate our thermal bridges for our energy calculations. But if it's not possible, then you can use this catalog. That was all I had about standards and methods. I know it was very quickly, but hopefully you grasp the basic idea. Now we will go to Björn.